In this chapter, we will introduce the fundamentals of metal casting. So we'll see different technologies allowing to do casting of metals. So first, we'll do an overview on casting technology, then see the main processes, which are heating and pouring. And after this, we'll study how solidification and cooling will take place. To start with, at the beginning of this course, we talked about different processes. One of the types is solidification processes. In such processes, the starting work material is either a liquid or is in a highly plastic condition. And then a part is created through solidification of the material. Solidification processes can be classified according to the type of material that is used. We can use metals, we can use ceramics, in particular glasses is widely used, or also we can use polymers and polymer matrix composites. In this chapter, we'll concentrate on solidification processes for metals. Now, as you can see here, this diagram is an overview of the different solidification processes. So we divide them into categories depending on the material used. So if we are casting metals, or if we are dealing with glass, or if you are dealing with polymers. Now, for each type, also you have different categories. So we'll see together in this chapter, we'll talk about expandable mold casting and permanent mold casting. And in next chapters, we'll detail other processes. Now, for casting of metals, the process consists to first heat the metal to its melting temperature, so it transforms to the liquid state, because as we know, liquid can be poured into a container, not like a solid. So, and will rely on flowing the metal by gravity or other force into a mold, where it will leave it to solidify in the shape of the mold cavity. Now, the term casting also applies to the part made in the process. So when we say casting, we can refer to the object produced. Now, as we said, we have three main steps in casting of metals. The first one is to melt the metal. The second one is to pour it into a mold. And the last one is to let it freeze. So we cool it and give it enough time to have complete solidification. Now, the casting process represents several advantages. First, it allows us to create complex part geometries, and we'll see in general that depending on the complexity of geometry, we will design different molds. So we'll see what is permanent mold, what is expandable mold, what is the difference. So this will depend on the geometry of the part. It can also create both external and internal shapes. You can make holes. We'll see how. You will alter the mold in a way to be able to create internal shapes also. Now, some casting processes are net shape and others are near net shape. If you remember in the introduction, we defined the processes if they produce waste or not. Okay, so we said that when we have near net shape, the waste produced is very limited. Okay, and casting processes can produce very large parts, and some casting methods will be convenient to mass production. Now, on the other hand, casting presents several disadvantages. So to start with, we have some limitation on the mechanical properties of the final product. We'll see why when we go through the detail of the process. We already talked about the accuracy. We have a problem for casting, and especially sand casting. The dimensional accuracy and surface finish is poor. So if you have an application requiring accurate dimensions, the use of casting might be questionable. And even if you want to use it, you need to, after having your product, it should undergo several other processes to reach the desired state. Other problems of castings is safety hazards to workers due to hot molten metal. So we should be aware when dealing with the casting process because we reach very high temperatures for the molten metal. And also we have some environmental problems related to the casting process. Now, the advantage of casting is that it allows to create very different geometries and very large scale difference in scale of sizes. So we can produce big parts and very small parts. For example of big parts that are made by casting include engine blocks, heads of automotive vehicles, machine frames, wheels, pipe, church bells, pump housings. So all of these can be made by casting. On the other hand, also it can be used to produce small parts as dental chrome, small status, jewelry, etc. Now, so first casting is usually performed in a foundry, which is a factory which is equipped with first. It should be able to make molds. So the first step will to create the mold that will allow us to do the casting process. Then we should melt and handle the molten metal. Third, we should perform the casting process. And finally, we have the cleaning of the finished casting. So when it's done, we do some cleaning operation to have it in the final state. And sometimes if you want to improve the smoothness of the surface, it can undergo other finishing processes to reach the accuracy desired. Now, workers who perform casting are called foundrymen. For this chapter, I prepared for you a list of YouTube links. In these YouTube links, you can find in detail how this process can take place, how we melt first the metal, how we pour it into the mold, how we leave it to solidify, and at the end, how we extract it. Now, the mold in casting will contain the cavity whose geometry determines the part shape. In the following slide, we'll see in detail what are the different parts of the mold. Now, of course, the actual size and shape of cavity must be slightly enlarged. So let's say you have to produce a simple example, a sphere of diameter 20 centimeters, for example. You will not design your mold exactly equal to your cavity in your mold exactly equal to 20 centimeters because we have what we call, when we have solidification, we have the phenomena of shrinkage. So due to shrinkage of our object when it's go from liquid to solid state, which will lead to a reduction in volume, we need to actually have the sizes of mold cavity little bit larger than the desired final shape to take into consideration shrinkage effect. So the actual size and shape of the cavity must be slightly enlarged to allow for shrinkage of metal during solidification and cooling. Of course, this is for external shapes. If you want to produce a hole, then the size of the hole should be slightly smaller because after shrinkage, the size of the hole will increase. So molds are made of a variety of materials, including sand, plaster, ceramic, and metals. Now, let us see some examples of molds. Here you have two different forms of mold, an open mold and a closed one. The closed one is used for more complex geometries, okay? While here, for example, when we use an open mold, we use an open mold like this, when the shape is simple in a way that if I reverse the mold after solidification, I can take it out and get my final part. However, for example, here, if you have such complex geometries, it's not possible to have an open mold. We should have a closed one. And in general, we can open it. So it's divided into two parts. So as you can see here, you have what is called the parting line, dividing it into two parts. You join these parts to form the geometry you want. And then once after pouring your metal and giving it enough time to solidify, at the end you just open your mold and you remove this part, and then you will be able to have your complex geometry. Okay, and sometimes if the geometry is very sophisticated and it's which will not allow possibility to open the mold, then we should do what we call the mold should be destroyed to extract the product. And if, for example, if you have a geometry like this here, if you have shapes like this, so here it's a little bit of larger width and then a smaller width here. Okay, if you want to open this, you cannot, it will destruct this part. Okay, so when you have sophisticated geometries, you might need to have a destroyable mold. So at the end of your solidification process, you destroy it completely to get your final part, and then you can use it just once. Okay, for such geometries, here you have a geometry that allows for you to remove the top without having any constraint. So as you remove it, you will get, your product will not be affected. So in this case, you can use this closed mold. Okay. Now, if we talk a little bit about the parts here, you have the pouring cup is the cup that we put in order to pour the metal within the cup. You have the down sprue, which is a channel through which molten metal will flow, and then it will go through the runner, which will take the molten metal to the cavity. Okay, so here you have the cavity that should be, if you want, filled with the molten metal. Now, a very important part is the riser. We'll discuss together after what is the function of the riser. In summary, the riser will help you to avoid any voids in your when you fill your cavity. So it can give you supplement of molten metal when needed. We'll discuss how the riser will operate together in next slides. You have here, as we said, for the closed mold, you have two parts that are joined through the parting line. Now, in a closed mold, we call the lower part a drag, and the upper part is the core. Okay, and you have that. This is your this part which is bounding your system is the flask, which is containing your mold. Okay, so these are the main parts of your mold. As you can see, this configuration is much complex than the open one. For the open one, you just have the flask, you just have your mold, and no need even for a runner, no need for a riser, because the geometry is quite simple. You directly pour your metal, it will directly fill the cavity, and at the end, when it solidifies, you turn it upside down and you remove your mold. Okay. Now, we have two categories of casting processes: expandable mold processes, which use an expandable mold which must be destroyed to remove casting. As I told you, sometimes if we have very complex geometries, it's not possible to use the same mold several times. So we have then to each time have produce a new mold. This might be challenging because you need to, at each time to have a new mold, but sometimes you don't have the choice. Okay. Now, mold materials can be sand, plaster, and similar materials, in addition to binders, which will have adhesive properties to hold the particles of sand, for example, within each others. You have permanent mold processes use a permanent mold which can be used to produce many castings. So this is the case of open and closed mold we have seen in the previous slide. Now they are made of metal or less commonly a ceramic refractory material. Now, concerning advantages and disadvantages, we have that more intricate geometries are possible with expandable mold processes, but as we said, it's on the manufacturing level, it's challenging to you need to produce several molds, and for each operation you need a new mold. Part shapes in permanent mold processes are limited by the need to open the mold. Now, permanent mold processes are more economic and can be used in high production operations because, as we said, we can use the same mold several times. In general, expandable mold processes are used to produce sophisticated geometries, and the production will not be very high, but the cost of the object produced will be higher. So depending on your application, you select the convenient type of molds to use. Now, in the following slide, we have again the different parts of a mold that can be a closed mold, where we can, at the end of the process, we can just open this part and release our object. Now we'll talk in detail about the different parts of it. So mold consists of two halves. Cup is the upper half of the mold, and rack is the bottom half. Mold halves are contained in a box, which is called flask, and the two halves are separated at the parting line. So these concepts were already explained in the geometry of the mold. Now, mold cavity is formed by packing sand around a pattern, which has the shape of the part. Here they are telling you how to produce your mold. Let's say you say, I want to produce a sphere of a certain dimension. So you bring a solid sphere of the dimension required, and then you start to pack sand around it. Okay. When the pattern is removed, the remaining cavity, and in general here, for example, if you want to have a sphere, you cannot use an open mold, you should use a closed one. It is the idea you put your sphere, then you pack sand from in the cup and rack parts. Okay. Please watch the videos. They will help you a lot to understand the different steps. So you can see all these steps, how we put the solid part, how we pack sand around it, then how we, at the end, after a certain time, we heat this system, and we have adhesives that will hold sand particles together. After a certain time, we remove the two parts, and we'll have already the shape of the sphere will be imprinted within the sand, which will form the mold cavity. So when you remove the pattern, the remaining cavity of your packed sand has the desired shape of cast part. Now, as we said already, the pattern is usually oversized in order to allow for shrinkage of metal during the solidification and cooling processes. And sand for the mold is the must and contain a binder to maintain its shape. So we have a certain humidity level within your sand, and you add some adhesives to maintain the shape of your mold. Now, when do we use a core in the mold cavity? Whenever you want to produce internal surfaces, you use a core. Okay, so the mold cavity will provide you the external surfaces of the cast part, but we also said that you are able to produce internal surfaces, and this will require then the use of a core that we'll introduce in a while. So this core will be placed inside the mold cavity to define the interior geometry of the part. In sand casting, in general, cores are also made of sand. Let me try to see a slide with a core. Okay, we don't have a slide here with the core, but I will tell you how we can do it. So if we go up to this one. For example, here, let's say you want to produce like a sphere with a hole, okay? Then what you should do, you should put within your system, for example, here, let's say you want to have any, let's say slot, okay? You can put within your system here, and you should fix it to your mold. So you can use something to hold it. And let's say you are putting a small slot like this. So this will be rigid. It can be made of sand with adhesive or any other metal. Okay. That of course have a melting temperature larger than the melting temperature of your metal, because it should remain in the solid state. So now when you fill your cavity, molten metal will be distributed around this core, and at the end, when you have solidification, you will have a certain hole or a slot produced within your final product. Okay.
Doctor, I have a question please.
Yeah.
ليش للانترنال بارت قلتي انه بنعمل مولد اصغر؟ مش انه اوكي
لا للانترنال ايه، لانه look انت look let's say you want to have here shrinkage يعني وقت يصير في solidification بتصير على طول in the direction towards the metal. okay. يعني البارت اللي من برا it will be will retract in this way, so it will be reduced in dimension. okay. بينما البارت الجوانية كيف تعمل shrinkage لهالمال؟ يعني شو بيصير فيها؟ يعني إذا عندك hole, okay, if you have a hole, at the end the whole diameter will be larger than the one of your core part. مظبوط؟ This is why you will design a smaller core and a larger cavity. What
okay,
has she idea?
Yes, تمام.
Okay. So so we're talking about the core. So as we said, the core will allow us to create internal surfaces, and it will be placed in the mold cavity to define the interior geometry of the part. In sand casting, we can use also cores made of sand. Now, what about the gating system? The gating system consists of the channel through which molten metal flows into the cavity from the outside of mold. It consists of a down sprue through which metal enters a runner leading to the main cavity. At the top of the down sprue, a pouring cup is often used to minimize splash and turbulence as the metal flows into the down sprue. Okay, so the purpose of putting a pouring cup, you know, in general, whenever you pour any fluid into a container, the pouring cup will help you to do the operation in a smoother way, because it will help to minimize any splash and turbulence affecting the filling process. Now, what about the riser? We said that the riser is a reservoir in the mold, which is a source of liquid metal to compensate for shrinkage of the part during solidification. And also another purpose of it is to avoid formation of voids within your final product. So the idea is that shrinkage will take place. Okay, one of the strategies to account for it is to oversize the mold cavity and reduce the size, of course. But also a good strategy to compensate for shrinkage is the following. So as you start to have shrinkage, this will lead to formation of voids and formation of, if you want, empty parts in your cavity. You can, to compensate for this, the riser can continue to, if you want, to provide your cavity with molten metal in order to fill these voids. Okay, and because the riser should continue to provide molten metal while solidification process, it should be designed in a way to freeze after the main casting. And we'll see how we can study the geometry of the riser in order to in a way that the metal in the riser will freeze at the end. To know how to do this, we should study the variation of the solidification time, and we'll see that it is related to the metal properties and also to the geometry. Okay, so of course the riser will have the same metal as the one filling the cavity, but the difference is that we can play with the geometry of the riser in a way to increase the solidification time of the molten metal in the riser compared to the cap. So we'll discuss this in detail through equations in coming slides. Now, concerning the heating of the metal, we can use, of course, it's a heat process, so we can use heating furnaces to heat the metal to molten temperatures that is sufficient for casting. Now, the heat required to perform this operation is the summation of three main parts. First, you need to raise the temperature to melting point. So at this stage, you are still in the solid state. After this, when you reach the melting point, you will go through the change of phase. So this heat then will be, if you want, absorbed in form of what we call latent heat. Okay, and in this phase, if you have a pure metal, you know, it's not an alloy, you will have no increase in temperature, but what will happen is that you have change of phase from solid to liquid. So here we have a mixture of phases. And at the end, when you reach, if you want, when you have 100% liquid, then when you supply heat again, the heat will be absorbed in sensible form, and you will have a raise in molten metal temperature to the desired level, which is the temperature required for pouring. Okay. So in general, in this phase, we have sensible heat. So heat is absorbed in form of sensible. You know the difference between sensible and latent heat. So if you have taken the thermodynamic course, you will know the difference. Anyway, I will discuss this again with you when we talk about the graph of variation of temperature. Okay, and we'll go through these details more. Any question on this? Oh. No. So an important step is to pour the molten metal. So for this step to be successful, metal must flow into all regions of the mold, most importantly, the main cavity before solidifying. So this is why we need to study what is the pouring temperature. It should be high enough to avoid, if you want, solidification in certain regions, blocking the flow of metal to the extremities of your cavity. Okay. This will be, and more the geometry of your final product is complex, this will be more challenging, and this will require a certain design of the pouring temperature in a way to, and your riser also, and you should design a convenient riser in order to allow molten metal to reach all extreme parts without blocking effects. Now, the factors that determine the success of such operation are the pouring temperature, the pouring rate, and the turbulence level. So we should study all of these. What should be the pouring temperature? It should be high enough to avoid any solidification blocking the flow of molten metal through all extremities of your cavity. The pouring rate, what should be the mass flow rate of pouring that is used, and what is the turbulence level of the when you do the pouring step. Now, the transformation of molten metal back to solid state will require, of course, to cool your to leave your system to cool. Now, it depends, as I told you, on the metal used. If it's a pure element or an alloy, you will observe different behaviors of solidification that we'll discuss together. Let us start with a pure metal. If you have a pure metal and you observe the variation of temperature with time, you will obtain the following graph. So first, we considered that we already performed the heating operation to reach the pouring temperature. Okay, so I reached the pouring temperature. Now I can pour my metal within the cavity, and as I pour it, we will start with the cooling process. So in the first step, it will cool from the pouring temperature to the solidification temperature or freezing temperature. Okay, so what will happen then in this phase? You have the state is liquid, and we say that we are performing liquid cooling. Now, when we reach the freezing temperature, then because it's a pure metal, so we don't have mixture of several, we don't have an alloy, so it's one pure metal. It's characterized by one freezing temperature. And then whenever we reach the state where we have 100% liquid, okay, we will start to have change of phase. So a part will be transformed into solid. So here, more you advance in time, the percentage of liquid will decrease and the percentage of solid will increase until reaching complete solidification. So here you have 100% liquid, 0% solid, while at the end of this phase, which is change of phase, you have, at this point here, you will have 100% solid and 0% liquid. And at any point in between, you have mixture of both phases and you have constant temperature. But it's true that you have a constant temperature, but your material is losing heat. It's losing heat, but we say that this heat is not in sensible form. Sensible form means that it's you have it with change in temperature. Okay, while when we say latent heat, this released heat is due to if you want a change in phase. You know that if you go from liquid to solid, what will happen? Your molecules will be more attached to each other, okay, and they will lose energy. They will lose part of their energy. While when you go from solid to liquid, you need to provide energy in order to destroy the strong relations between your molecules. So this is, if you want, we already introduced this concept when we talked about the type of bonding in molecules, okay? And we have seen that in case of solid, these bonds will be much stronger than in case of the liquid, and for liquid they are more stronger compared to gas. So whenever you want to go from solid to liquid or from liquid to gas, you need to provide energy to destroy these bonds. So this energy, instead of giving you a change in temperature, will destroy or form bonds depending if you are going from solid to liquid or from liquid to solid, etc. Okay, so this is called, in this phase, we say that the exchange is in form of latent heat. And we can express latent heat and sensible heat, okay? We'll see together what are the equations for latent heat and what are the equations for sensible heat. Now, once we reach this point, we consider that freezing is complete. This point is the beginning of freezing, and we say that we can talk about local solidification time and total solidification time. Total solidification time will start from the instant you pour your metal. Okay, so from the instant you pour it until you obtain 100% solid, this is the total solidification time. The local solidification time is the time needed to have change of phase. Okay, so this is for the terminology. Now, once you reach 100% solid, you will still cool because the temperature is, the freezing temperature is relatively high. So you need to continue cooling. And now we call this phase solid cooling. And again, you switch to sensible heat mode. So you are losing energy. And this loss of energy is in the sensible form. So you will observe a decrease in your temperature. Okay. Any question on this graph? Now, due to the chilling action of the mold wall, a thin skin of solid metal is formed at the interface immediately after pouring. Skin thickness increases to form a shell around the molten metal as solidification progress. Rate of freezing will depend on heat transfer out of the mold as well as thermal properties of the metal. What are we talking about here? To understand more, let us look at the following figure. Consider that you have you poured your metal within your cavity. Okay. Solidification process will start first at walls level. Why? That's due to gradient of temperature. You know that your walls are relatively cold, and when you have contact between very high temperature, which is the temperature of your poured liquid, and the small temperature of your wall, due to this difference in temperature, you will have a faster solidification in these zones. And this will lead, because it's a very fast process, so like it's a shock, you will have formation of what we call characteristic grain. These are grains. So in general, you observe grain structure near your boundaries. While towards the interior of your cavity, you have more organized pattern, because they will take more time. They will have enough time to solidify. Here you have a sudden solidification. So this structure is a characteristic grain structure in a casting of a pure metal. Show randomly oriented grains of small size near the mold wall and large columnar grains oriented towards the center of the casting. This is because, as I told you, in this part you have more, the solidification process is taking its time, while here it's more sudden, which will lead to formation of random orientation grains and of small size. So you can see that the size is much smaller compared to your other grains in form of columns. Now, on the other hand, okay, if the solidification process for an alloy is much more complex, okay, and we will discuss it in detail together next time. Plus, we will do some problems to, if you want to practice on sensible and latent heat, how we can calculate them, how we can know the time needed for solidification process, etc. Okay, so see you next time. Thank you. Any question before we stop? Okay, yeah, let's see you next time.
No questions.
Yes?
Thank you, doctor.
Okay.